Okay, so let's start. Welcome to the next lecture from Effective Software. Starting from today's lecture, we will make more impression to Java, and we will look how virtual-based systems are working. So it's not only about Java. The same is applicable to .NET and other stuff like Kotlin, everything which is using some kind of virtual machine or specifically Java virtual machine. It doesn't matter. It's very similar everywhere. So what we will talk about today is, after some introduction, we will talk about memory layout, which is different than in C language. Then we will talk about the bytecode in detail, about difference between disassembler and decompiler. Then we will focus on just-in-time compilation and various levels which are inside, optimizations applied, and so on. Then I will highlight a save point, which is a key moment in any virtual machine. And finally, we will talk about profiling, how you should profile and how you should approach that. As I mentioned, virtual machine model is not only about Java. The main thing which is different from C language is that the source code is compiled into virtual machine bytecode, which is some kind of hardware-independent representation precompiled, which can be then executed using a specific runtime environment, some kind of program, which is usually specifically installed for that particular architecture of the computer, whether it's ARM computer or the standard RISC computer, or whether it's some kind of mobile phone, it doesn't matter. That runtime environment is specific, but the code of your application is hardware independent itself. And the execution of the bytecode is done in default in interpreted mode, which means that there is a kind of interpretation. Take one bytecode instruction, evaluate what it is, execute it, then take another instruction, and so on. Another execution is compiled, where your bytecode is automatically compiled in that just-in-time compilation into natively based assembly code for that particular architecture where the runtime is running. And the benefit of this later compilation is the fact that then that runtime can automatically, using the capability of the system, can be used for the optimization, like SMID instruction and other optimization techniques. Yeah, here you have a comparison of bytecode and assembly code in general. Let's move to the next slide. This is the basic layout of the memory used in all virtual machine approaches. The key is this division, which is on the left side, there is a thread-specific part of the memory. So every thread has some kind of dedicated piece of memory, where usually a stack is stored, like in C language. The difference here is that there are two stacks. Stack for the virtual machine and stack for the native execution. Every code, even it's running in virtual machine environment, it has to interact with the hardware. And all this interaction with the inputs, outputs, networking, etc., is done through the native libraries, because it has to go to the kernel code finally in the operating system and access the hardware. The stack of the virtual machine, so for the native execution, that native stack is used. For the virtual machine execution, a stack for the virtual machine is used, the left side, and that stack contains frames. I will talk about frames on the next slide. On the right side, there is a kind of memory which is shared by all threads together, and it's divided into two main pieces. One is heap. The heap memory contains dynamically allocated objects. Anything which is created like new in your code, it's stored in this memory. In a non-heap memory, there is two parts: metaspace. Metaspace contains the class definitions. Simply, you will see what it is during the today lecture, and also dynamically generated assembly code for your application. And also on the left side, there is other native memory allocations, because you can allocate some kind of data structures directly outside of heap memory, which have many benefits. We will talk about that during some next lecture. So now about frame. Each thread has own stack, those two stacks, one stack for the virtual machine execution and one stack for the calling native code. So you have to know the difference between stack overflow error and out-of-memory error. Out-of-memory error is thrown when you try to allocate dynamically new object and there is no more space in your heap area. On the other hand, stack overflow error is generated when you have a lot of deepening calls of methods, for example, recursion of your code, and your stack is not big enough, and there cannot be allocated additional frames, because every frame is created when some method is invoked and destroyed automatically when execution returns from that method. There are two types of frames. Interpreted frame, used exactly one frame per method during the interpreted execution mode. And second kind of frame is compiled frame. That compiled frame could be for one or multiple methods together, because one of the basic optimization technique is inlining. It will reduce calling and other stuff and jumping of the processor, returning and so on. So all frames of inlined methods are combined together into single compiled frame. The frame size is determined at the source compile time for the interpreted frame, and for the native code, for the assembly code, it's during the compilation into assembly code, so during the just-in-time compilation. What is inside? There are multiple things. Variables. So what is variable? For any instance method, the first parameter of the variables is this reference to the object on which that instance method is called. If it is static method, this thing is missing, so it's not used. Then input method arguments, and finally local variables. So all this is kind of by default 4-byte area for longer data types like long, references, doubles. 8 bytes is used. The next piece of the frame is operand stack. Operand stack contains arguments for all operations. You will see how a virtual machine executes instruction in interpreted mode on some next slides. And finally, there is a reference to runtime, to the class in which that method is implemented, because there is key thing inside, and that's the constant pool, the definition of all constants in your source code. So the names of the methods, descriptors, signature of the methods, also some static variables are stored there, etc. So here, just to summarize that, you can have two threads in your application. You have the heap, which is shared across those threads. Each of the thread is executing some methods, two methods in this example. Those methods could have in the local variable pointers to the objects in the dynamic memory, dynamically created objects like these arrows here. And also objects themselves can have references each others. That reference in Java, that arrow here, is internally called as a OOP, which stands for ordinary object pointer. Why that there is a specific data structure? Because depending on the method how you will start a runtime environment, the size of that OOP could be different. It could be either compressed, just 4 bytes, which is saving a lot of memory, or the regular 8 bytes. To access the large portion of the memory. We will go through that later as well. Here is the slide about how a virtual code or bytecode is executed inside virtual machine. It is internally used that stack-oriented approach. What it means, here you have some simple algebraic example, some summation, multiplication, and so on. So this is the stack, the second row of this table, and here we have inputs. Timeline goes from the left to the right. So in order to evaluate this simple expression, first 2 is inserted on the stack, then 3 is inserted, then addition method is called. Addition method by default works with the values on that stack, so automatically pops 2 values, and the result is inserted there, and so on. So that's the way how the interpretation works. After the compilation into native code, for sure it's different, but in interpreted mode it works like this. It's crucial to know how it works because there are moments that the switch over from interpreted into native code can happen not only at the entry of the method, but also inside the method. And in that case, values from the stacks are remapped from this internal stack into register, into some different representation used for the compiled stack. Okay, now there are some Java virtual machine bytecode instruction. In virtual machine for .NET, it's very similar. It's a sequence of instructions composed of opcode, operation code, and some opcode specific parameters. The opcode itself is in almost all cases just single byte only. That's the reason why it's so efficient to use this generic representation. And we can see it on this slide. There are various types of the operations possible to cover everything. A manipulation of the stack, arithmetic, logic operation, and so on, calling of methods, object manipulation, stack management, transfer the code, some conditionals, invocations, some go-to instruction is important because it's internal stuff. It's not the go-to which is used by the programmer, but rather when you have some cycle, there has to be instructions to jump somewhere else in the code. That's the go-to here, and so on. Many of these instructions, which are some examples are in the brackets, use prefixes and suffixes. This defines simply the data type on which these instructions are working. So this is clearly mapped to the primitive data types, except the A, which is used for the reference. So this is double, float, character, boolean, etc. So, and A is used for the reference. This is also used for the return instruction, return from some method. So A return means that method returns a pointer to some object. So here you have some comparison of how the bytecode in the readable form looks like on this right side, compared to the assembly syntax. In this case, it's AT&T syntax. So it's, for example, this movement is from RAX register into R8 register from left, from the first argument to the second, because there is also Intel syntax, that's vice versa. So now let's look to the details. After compilation of any source code, there is created a class file. For every class, there is one class file, which contains many stuff which is mentioned here. Aside, there is also version for sure, because there are different versions of the Java language and virtual machine support as well, so that version is there as well. Then there is a constant pool. We will look to the details, the definition of the class itself, implemented interfaces, fields which are defined in that class, methods which are defined, including the bytecode itself, and attributes which could be something like annotations and other stuff there. So let's look to the first example in this lecture. The first example is a simple DTO object, some data object. Employee, which is using generics. Here, generic is used for the data. Then we have ID, we have some constructor, we have a setter, we have a getter. So just a very simple DTO object with two properties. If we compile this code into bytecode, this is just the ASCII representation of that bytecode. And you can clearly, this is the beginning of the file. You can see the offsets on the left side. You can clearly see that there is some readable form in the first part of the binary class file. And that's the constant pool. There exists a disassembler. That's the tool which is included in every development kit in all versions, Java P. And you can use that to just disassemble binary form into human readable form. It does nothing else than just the rewrite binary information into human readable form. So if we use this disassembler to our example here, this is what you will see. So let's move to the correct place. Yeah, so if we disassemble that employee class, which was typed, you can see that there is a version information read here, some flags that it's a public, it uses a super constructor, and so on. Then there is this constant pool that's mapped to the readable piece of that binary file. And that is using references to itself in many cases. So here you have a method definition. That's the method init, which stands for the constructor, is using empty input arguments. So it's referencing 6. 6 is saying class definition. Class is referencing 30 here, and 30 stands for the Java lang object. Everything is automatically derived from object in Java, even if it is not explicitly written there. So this, for your convenience, this disassembler automatically into this command includes that dereferenced version of the definition. And you can see so on many other stuff. Usually all definitions are in UTF-8 representation, so it can store anything. What is interesting in this example is that even if we are using in Java generics, type-based class definition, you can see that update method, for example, the setter we had there, is using two arguments, and one is object, and the second is integer. Interesting. The first should be typed, but in this case, it's a descriptor which is used internally in virtual machine for the execution, and during the execution, type things are not checked. Those are used only during the compilation. Method signatures are used only during the compile time, not during the runtime time. During runtime, all objects are based like an object, and that's fine. So those parameters are object automatically. So this is a continuation because the disassembled version of that binary representation of our example class is long. So it continues here. So this is just the beginning. This is the continuation of that disassembling. So here you can see definitions of the fields defined in our class, data and ID. And there are, in almost all cases, descriptors and signatures. Those are two different things, as I've already described. And here you have that what I've already said. For the primitive types, signature is exactly the same like a descriptor, so it's not needed at all. What will be more interesting is further continuation. So for your convenience, I've put here always the source code from which this is resulted. So this is, as you can see, this is simpler getter. So getter, which returns the data from the object, and in our source code, it was using generic for the return value. In here, you can see that descriptor says it returns object, it is public, and here is our code of this method. First, as I mentioned initially, the size of the frame for this method is determined during the compile time. So here you can see the stack size for this method is 1 needed. There is argument size, input arguments to this method 1. Why there is 1? That there is no input argument in our method defined. But we see here 1. Does anybody knows why there is 1? I've mentioned that already. Exactly. It is non-static method, so there has to be this. So this is automatically passed there, so that method itself knows from where data should be taken. Otherwise, it's unknown. So there is the reason. That's the reason why there is 1. And the size of the local variables is 1 as well, because local variables is always sum of the argument size plus if some really local variables are needed. In our case, not needed. And you can see that the compilation, the bytecode of this method is very simple. Just these 4 bytecode instructions. This offset on the left side represents the offset in bytes from the beginning of the method. So in fact, it's using 5 bytes for the definition. You have those 5 bytes here down as well. And you can see that it's loading into the stack reference from the local variable 0. That's the first one, that's the this. So this is loaded to our operand stack. Then get field is called on the operand stack. So it automatically pops this reference and knows I have to find #3 is a reference to constant pool. It's a reference to this, so to the definition of the data field. And this results into value on the stack, which is the pointer to that data. And finally, a return means this method returns that pointer which is on the stack. So that's it. That's so simple code. So let's look to more complex. In this case, it's a constructor of the method. So again, here we have our source code. Constructor has 2 arguments, and it internally calls the updates. So you can see how such code looks like in Java bytecode. In this case, it has 3 argument size. Why? There is this newly allocated object plus this 2. That's the reason why there are 3. Locals are 3, no more local variables, but using stack size 3 in our case. So in this case, 11 bytecode instruction is needed for the constructor. You can see that even our object was not explicitly saying extend object. First thing which is called there is a constructor of object, and then update method is called here. And the same you can see here for the update method, how it looks like. Again, notice differences of the stack size, and you have here the code which is implied from this source code. What is also here and is useful is this line number table, which is interesting. Even your code is not compiled with any special options, so just default compilation. There is a reference of this bytecode instruction to the source code line number. So line 7 was for the bytecode instruction at the offset 0, which is the first one. Line 7 is the definition of the constructor. Why? Because there is that call of the super constructor automatically. Line 8 here, call of the update, you can see it's offset 4. So that code starts from the offset 4 and so on. The closing bracket here, line 9, offset 10. Interesting stuff, which can be used for the decompiler. So there are 2 things. Disassembler. Disassembler just writes a binary representation into human readable form of it. Nothing else. So this code is read. So if you are looking or how some third-party application is working, you can use this disassembler and check what is happening inside. Or better, you can use decompiler, which tries to derive from the binary form of that class, tries to derive back the source code. So the reverse process of the compilation. One example, that's not by default part of the development kit. I have here one example, Procrayon application, open source decompiler, which decompiles Java bytecode into source code. So here we have our original source on the right side, and the result is here on the left side. You can see that it's pretty much our original code, even it was not compiled with any special debug information, anything like that. The only differences which are there, you can notice here, is the name of the local arguments or variables, because those are not included in the bytecode. So those are generated somehow automatically by the decompiler itself. So instead of ID, we have n here. Instead of data, we have type. But it doesn't matter. You can use this decompiled code for your modification and further compilation back to the compiled class. Why it's useful? For example, you have some game which is using Java virtual machine. It doesn't need to be Java. It could be Kotlin, whatever, Scala, whatever code inside. You can decompile that code because you always have it. You can check how it's working. You can modify it, add credits, take certificate for communication with the server, whatever secrets you need. Modify that, recompile just the modified piece of your code, exchange your modified class file inside the archives of the application, execute that modified application, and so on. That's also possible in C language, but usually you have to go there into assembly. That's doable, but in assembly a lot of relative offset is used. So that's usually slightly problem to not to break down the code with the moving some pieces and break down the offsets, relative offsets. In Java, it's much easier. There are ways to make it harder, but you cannot stop to do that. That's always possible. So let's introduce our second example, which will be used through the rest of this first lecture. So here we have the source code of the example 2, and there is no enclosing class, just to omit the space needed for it, and we have just two methods here: days in month, self-describing, returns number of days in particular month and year. Year is needed for the leap years, right? So you can see that for the February there is year used to compute what is the number of days. What is important here is that this method returns integer with capital I, which is object-based integer. That's crucial for our further demonstration of this code. But usually this should be primitive integer, but to demonstrate some optimization techniques used inside virtual machine, there is intentionally inserted object-based integer here. So at the return, we intentionally return create integer with the return value. Done. If there is provided a wrong month, illegal argument exception is thrown. That's also interesting. You will see that in the next code. Then the second method is compute. Some kind of, again, demonstration-like method. So you can see there is a huge for cycle, million iterations, calling days in month method, and accumulating the result into O local variable, which is finally written in the form of the primitive integer. What is important in this example, you can see that these are somehow internally, it's called as a, let's say it as a constants from the perspective of the loop, because they are not changing. So we are always calling it for the April month and the constant month inside, but in million cycle. And we will see what is looking during the execution of that method through the rest of this presentation. So first, bytecode. So here we have our source code of the days in month method. And you can see how it looks like when we use not decompiler, but rather disassembler the bytecode, how the bytecode looks for this method. And you can see there is some kind of table switch with the jumps into proper locations, and you have here the mapping of the code, which continues on the next slide. What is here interesting, that it's really using some local variables, because locals is 3, argument size is just 2, so it requires one more local variable, and that would be probably the return variable here. And here is the continuation of the disassembled form. This part here, the first part here, is just the representation of this default case, which is outside of the defined months, throwing illegal argument exception, unknown month, and input arguments. You can see that that code is much longer. Why? Because first you have to construct the string. In Java or the virtual machine, all string representations are immutable. Those cannot be changed. So first you have unknown month string, and you would like to concatenate that with the month. That's not possible using the string, because you cannot modify that. So internally, automatically, string builder class is used, which is mutable form, which at the end result into toString, into immutable form of the final string. So those pieces are accumulated there, and once it's final, string representation, which is immutable, is created, and then illegal argument exception constructor is called, and so on. So that's the code for this. And code starting here to the end of the method returns a new integer, so calls the constructor of the integer, passing the value, and finally return the reference to that newly created integer. We already talked about line number table, but in this example there is another piece here called stack map table. This piece is there because this method contains branches. We have that case structure, that switch with multiple cases. Those are jumps. And also we have some shared piece of the code at the end here, where we are constructing the object-based integer and returning. So there is another branch from this break to the end of the method. And because of that, there is this stack map table, which define variable types in the frame for every target jump position, so that virtual machine can clearly test and ensure that the data types are manipulated correctly. That's something which is not inside C language. You can easily put the data to the memory like a byte and finally read it as a double, and you will get some mixed value because you don't know simply what you are storing there. That's not possible in Java. So it ensures that the correct data types are manipulated and interpreted as right values from the stack. Why it's only from the target jump position? Because then through the code it's clearly defined what data types are on the stack, what is inside the variables in that frame, etc. So that could be easily derived. And this is internally used for the verification during the execution that correct data types are used and not misaligning of the data is caused there. Here is the continuation of our example, our compute method. You can see the bytecode on the left side. Here you have highlighted for cycle, as mentioned on the first slide. Here is a goto internal instruction ending the cycle and jumping back to the beginning, where there is a comparison of the ending condition. If it is matched, we are jumping to the outside of the cycle. If not, we perform the internal piece of that cycle, which is called of that days in month method. Conversion, what is here interesting, is int value, automatically calls int value. Why? Because days in month returns object-based integer, but our accumulator is primitive integer. So there is unboxing from the object-based to the primitive, and that unboxing happens automatically using that call of int value. and so on. And what is important to know from these examples is that you can see that there is no optimization during the source code compilation. So once the source code is compiled into bytecode, it's really the rewrite. So if you write your code wrongly or have too complex algorithms, it will be too complex in your bytecode as well. And keep in mind that this initial bytecode is really the thing which is executed in interpreted mode inside virtual machine. So the resulting code is as bad as it was in your source code. So no optimization techniques applied up to this moment. Yeah, this is just the summarization what I said. Yeah, no optimization techniques. Optionally, you can use that bytecode could be really manipulated. So you can do compilation, and that bytecode could be somehow tweaked, modified, and another bytecode could be created. One of that process is obfuscation, make harder decompilation, so really return from the bytecode back to the source code, using the obfuscation. Many obfuscators, like here I have one example, ProgVart obfuscator, that includes also bytecode optimization techniques, like a shrinker, compact code, which is not needed, remove that code, never called that code, that piece of the code, so remove it completely. Also optimizer, modify access patterns, even inline some simple methods to the calling methods. And also, because it's obfuscator, so it does the renaming, layout changes, and also finally verify that the resulting class behaves exactly same like the input, but it's somehow tweaked and in unreadable form. So depending on the quality of the obfuscator, the compiler could start failing in many cases because the pattern of the code could be changed, and then the compilation is not easy to understand what was really inside the original code. You can test yourself on our examples how it will look like the resulting bytecode after that. But the key information from the piece up to here is that the source compilation by default doesn't contain any optimization. So it's as bad as the original source code you created. Now let's progress to the just-in-time compilation. Just-in-time compilation runs in runtime. Up to Java 17, there existed AOT, ahead of time compilation also, which can be used by programmer to create assembly code in advance before the execution of the application for that target platform. But it was removed due to the maintenance cost. It was too complex to maintain this ahead of time compilation, and also there were not big benefits of this ahead of time compilation, as you will see, because it cannot use these adaptive optimization techniques, which are included in just-in-time compilation. Adaptive compilation, there are some levels of compilation you will see on the next slide. Specifically, there are two types of compiler, and there is some trade-off balancing between time to compile into assembly code and really interpreting the instructions. So it has to decide when it is worth to really start the compiler to produce native assembly code and finally use that native assembly code because you spent resources of that computer to create that native code. So it somehow monitors hotspots. That's the name of the famous original Oracle virtual machine hotspot that's coming from this, monitoring hotspots in your applications, and for those hotspots creates native code. Key thing here is that it can do risky assumptions for the compilation. It can completely skip the code which was not used up to that moment, but that risky assumption is accompanied with the method of dynamic recompilation if it is needed. If it is called with different arguments and some different piece of the code is really needed, then automatically it unwind back to the interpreted mode and recompile it in the meantime into different version of that code. So it can optimize branches, inline expressions, omit code, change the data types, whatever is needed. And if some assumptions are no longer valid, it automatically rewind back to interpreted mode and recompile that into better form if needed. I've already mentioned there are two types of compilers inside into native code, C1 and C2. C1 is pretty fast. C2 is slower, sure. On the other hand, it includes just the few optimization techniques like some simplified inlining, inserting the methods body into different methods. For sure, it uses CPU registers because that's the fastest optimization technique. Instead of accessing the memory, you can store local variables into registers of CPU, and those are the fastest memory you have in your computer. It uses a window-based optimization technique. That window have limited size, so it looks through the bytecode and then rewrite that bytecode into better form using that window size. Resulting in faster execution, not into the smaller code, but rather faster execution. So all of these techniques are usually focusing on the speed of execution. C1 compiler also use vector operations, simple instruction multiple data, SIMD, like array copy, multiplication of 8 integers at the same clock cycle, resulting in 8 integer results, for example, in single cycle, just the parallel operation. That vector operations in C1 are used in intrinsic function. Intrinsic functions are some predefined, well-known libraries used in many code, like math library, array copy internally, string comparisons, everything. So there are predefined patterns written in the just-in-time compiler source. By default, you can study that internals, how it works, how it does the compilation, what are the optimization techniques in OpenJDK, because it's publicly available as open source, and you can really look how such compiler works and what is produced as a result. On the other hand, C2 compiler, as I mentioned, it's much better, but on the other hand, much slower, like 5 times, 10 times, depending on the complexity of the method, compared to C1 compiler. So just-in-time compiler has to adaptively balance the trade-off between the time for compilation and really what is needed. So that's usually why this kind of compilation levels are used, and the standard path is usually no compilation at all. So if you execute some code for the first time, it's run in interpreted mode. After some time, it runs C1 compiler. C1 compiler in various configuration options. One of the options is just compile it into native code and let it be. That's used for simple method. If the method contains some branching, then there is also invocation and back edge counters, so that further compilation knows where the code is usually running, because you should know from the hardware description of the CPU that the slowest part of your computer is first the access to the memory. So that's the reason why there are caches, and all your code should fit into the cache. Otherwise, there is a lot of clock cycle needed to access the data. Another thing is, if CPU use internally superscalar architecture and decodes many instructions in advance until it's executed to speed up the further execution. And if there are some conditional branches, CPU have problem because it has to decide go that path or that path, and if it miss, it will cost a lot of CPU cycles. So that is used here internally for the tracking, knows where we are jumping usually, and do not do jump into the code which is called in 100% times or 99% of the times of that method. Make it pass simply through, and that's it. And only if there is some specific argument which goes just rarely there, jump if needed. So it can reshuffle the code. Also, there could be this MDO, that stands for the metadata OOP tracking, which analyzes type of the pointer, type of the data object at the end, because usually if you call some method, it has to use virtual tables of the implementation. Is this overridden in this class? Is it a method from this class? One thing. Another thing, this accept, for example, argument which is kind of object. But in fact, it could be anything, any kind of object, because everything is object-based in virtual machine. And depending on that type, there could be branching in the code. And if this information is tracked, it could be used in further levels of compilation, and that's what is happening there. So you can see these numbers, 0 up to 4, where the 4 is used for C2 compilation. Usually, C2 compilation is the ending, the best optimization. All kind of optimization mentioned here. We can show some of them. What is crucial here is escape analysis. We'll talk about that sometime later. Also pattern-based vectorization. So if you have some cycle in your code, source code, it can automatically derive, it costs time for the compilation, but it automatically derive, yeah, I have CPU supporting this 1 kilobyte vector operations. So let's rewrite that into vector operations and make it much simpler. That's what is happening inside C2 compiler. So it's very advanced thing, but it speed ups the code. So it's really then affects whether you have this architecture, that architecture with that support, because your code is a native code which is executed there could be really different with the different speed. The standard path of the execution is 0, then usually 1 or 3 if it is more complex, and finally 4 if that piece of code is used frequently. It's a hotspot in your application. One more thing on this slide, on-stack replacement, OSR. That's the optimization technique used inside the method itself. That's the reason why in our example we have that 4 cycle with 1 million iteration. On that, I will demonstrate how virtual machine exchange interpreted code into compiled form in the middle of the method, not just at the entry or exit level. The reason this slide just summarizes why it's important to also study the assembly code in your Java, Scala, whatever kind of application running on the virtual machine. Because you can see if your source code is written well so that it can be optimized by that execution for the speed, data fits into caches, properly vector programming is used there, and also what is the size of the code, what is working well, because you can usually help the compiler. If you slightly rewrite your source code, you can help a lot of your compiler to make it better for execution later. So first, let's look to the leveled-based compilation, that adaptive compilation. If you use these arguments for the runtime, you will see a more debug information. Those debug informations are here. What is important for us is this column, this number, and this reference to the class. So I've already highlighted pieces from our example. And you can notice in this listing the standard compilation path. So initially it runs in 0, interpreted, not listed at all. Here you can see 3. In the table on the previous slide, 3 is C1 compilation, including invocation and back edge counters, plus that method data tracking. That's what's happening on this slide. Yeah, you see that, but I don't. That's simply the number 3 in the listing here for the days in month, because that's the method which is inside our cycle. So that's the first one which is identified as a hotspot in our application because it's called too many times. Later you can see that after another some time you can see there is 4 C2 compilation on the same method, because it's called even more, even after C3 compilation, which is not that much optimized. The code is still used a lot, so it is worth to compile it better. Another thing you can see here is this made non-rentrant, means compilation into C2 result is done. We no longer need C1 result, so it simply means drop the previous code which was used for some time. And here, this percentage symbol, the important stuff, is on stack replacement, where here you have add offset 10, add offset 10, 10, this -2 is there because it's a drop of the previous code. So after some time, because there are those million cycles, virtual machine decides, okay, internal part of that cycle is really cold enough, and it's a hot piece of this method. So it is worth to do C1 compilation, replace that on the stack during the execution, run that native code. After some time, it's even decide, okay, it's still used a lot. Let's replace it with even better code and do the C2 compilation. Also, as a result of this internal on-stack replacement, there is scheduled compilation of that method as a whole. Even it was called only once in our application. We called only once compute because it doesn't know that there will be no further invocation. So it decided internally, let's compile it even better as a whole method. So now let's look into the resulting assembly code. It is possible to display assembly code using these options. In our examples, everything will be in AT&T syntax, as mentioned, using 64-bit machine. So what we have here we have the result of the level 3 compilation, which is C1 with invocation package counters and metadata OOP tracking. The reason was also mentioned then. Reason is it was hot and was called 256 times before as interpreted. So that's the reason why internally virtual machine triggers C1 compilation at the level 3. And you can have here really the code of that architecture. That's the, I think it was executed on the Intel Haswell architecture CPU, 64-bit, and so you have here the resulting code. At the beginning, you see the mapping of the arguments to the register, so it helps you to understand what is where, and then there is a sequence of the assembly code resulted of our days in month. This is days in month method first. And what we can see here is some stack initialization that's very similar to C language result of the compilation. You have to always allocate the frame. At the beginning of the method, you allocate the frame size needed for the arguments. That's happening here as well. Then there is the invocation counter. So here it's incrementing number of invocation of this method. So there is additionally added code into that native code, incrementing counter for every execution. And once that execution reach 1 kilo, in a really kilo, to power 10 invocations, it triggers C2 compilation. So that's the hot spot tracking again. If this method is called enough times, let's make it suitable for the further C2 compilation. Here is just the code for the switch. So for every month, you can see, it's compared with 1, 2, 3, 3, and if it equals, jump to additional target position. So not enough optimization techniques here, because if you are always calling with month 12, it has to go here up to B hexa, which maps to month 12, and do the jump. And this is default jump. This code is what we are interested because we are always calling that for the month 4. So this is the resulting jump position for the month 4. So you can see, okay, it's assigned 30 to some register. That's it. Then there is a jump to the final piece of that method. And what is interesting there is an inline TLAB allocation. What it is, TLAB stands for Thread Local Allocation Buffer. So that's the way how a virtual machine can very quickly allocate new dynamic object on the heap, excluding any synchronization with other threads, because it's a local allocation buffer for that thread. So it can easily use a technique which is called bump the pointer. Just increment the pointer to the free space with the size of the object, and you have newly allocated object, the quickest way which is there. So there is here is the integer allocation and the object initialization, some nulling and header filling. Every object in Java has a header. So the standard object has 12 or 16 bytes header size. There is a 8-byte marker. All is for 64-bit JVMs. Today's 32-bit JVMs are almost not used anywhere, even on the mobile phones. And then there is 4 or 8-byte class reference. There is a class with K. Why K? Because it's internal representation. It's not the class with C, which stands for the user representation you can access. Internal is with key to distinguish that. Why there is 4 or 8? Compressed OOP or not compressed OOP. If it is using smaller heap size, up to 32 gigabyte, then thanks to the alignment of every object start address, because it's aligned to 4-byte address always, you can omit those bytes which are not needed, or 8-byte address, those are 3 bits. You can omit those 3 bits, and you can fit pointer into 32 gigabyte sized heap into 32 bits only, because you can omit easily those lowest 3 bits. So that's the reason why in some cases just 4 bytes are used, and you can more effectively use your memory in your application. In case if your heap is bigger, it has to use 8 bytes. This is the standard object. If it is array-based object, there is also array length, because Java is ensuring that you are not going outside of the range. That's our quite well-known index out-of-bound exception that happens after the verification that we are trying to reach outside of bounds. That's something which is by default not part of C, and you have to do that yourself to not to read or write, modify some memory which is not that object. Here is another example. That's the continuation of that method, because here we just allocate the object, but we have to call all constructors, all super constructors. And you can see in the listing that there is an integer constructor, number constructor, finally the object constructor. And because there are invocation counts as well, the code is not that simple. So you can see that the calling of all constructors which are in line here is that long thing. And here is the finally assignment of the integer value into object-based integer. And finally, the method ends with this simple code. There is a return at the end, but before there is a stack deallocation, cleanup, yeah, and there is also save point. So what is save point? Save point is a special moment in virtual machine where all OOPs, ordinary object pointers, are in perfectly described state. Why it's needed? For some global manipulation like a garbage collection, print thread dumps, do heap dumps, do debugging or whatever. In that moment, every OOP inside, which could be in some register in CPU, for example, at that moment, have to be in a really well-described form, and virtual machine needs to know where those pointers are. Why? Because if you do some kind of object modification, for example, garbage collector, reallocate object somewhere else, you have to update all references to point to the proper location. And those references, you need to know about them. And also you have to update registers, local variables, whatever, where it's all this position have to be updated. That's the save point situation. What I've described is a global save point. There also exists local save point just for the single thread, because global is for all threads, globally for the whole application. Local is for the single thread, and that's usually used for the optimization or the on-stack replacement. In order to do on-stack replacement between C1 and C2, you need to know how to map values from that execution of C1 into C2 compilation. Where the save point is, in interpreted mode between any two bytecode instructions, in C1, C2 compile method, by default, at the end of all methods, that's what we see here, end of our methods, save point pool check. Why? Because you don't need some special description where OOP are in that case, because OOP could be only in AX register as a return. If that method returns a pointer, that's at that moment at AX. Everything else, all local variables are disappeared, input arguments are no longer needed, so at that moment save point is. Or at the loop back edge, so at the target position, every loop back edge, so that's mapped to the stack map descriptions. At that moment, that description in fact says this is pointer, this is pointer, this is in register, this is at that position of the frame, and so on. So that's perfectly described state. One more comment here, JNI, Java native interface, way how Java execute native code provided, for example, from C language, assembly, whatever, external stuff. In that case, thread suspensions is not permitted. Suspensions occur when that thread returns back to the virtual machine world. So when you do sysout or whatever, sysout is executed, and once it returns, that's the moment when it can sleep. Related to save point, there is a crucial parameter called as a TTSP, time to save point, how long it takes to enter the save point. So here we have examples. We have a profiler, that's the reason why it would like to do some kind of breakpoint or whatever. And we have multiple threads. Every column here is one thread. If it is at J, it's a Java thread. If it is at JNI, it's currently in native code, external of the virtual machine. And this is the moment where the profiler says, I would like to have a global save point, stop everything. And then this method execution, after some time, reach the end. So save point is detected, suspended. This is currently yellow, means as described here in the labels. You can see that it's descheduled. It's not executed at that moment because you have usually less cores in your system than you have requests for the execution. So this was not scheduled. After some time, gets scheduled to the CPU, reach the moment where the save point can be reached, done. This is the same. This is not applicable until it returns back to Java. So this is the moment when the global save point occurs. And this difference between the initiation and the occurring is that time to save point, TTSP. And that's non-zero in all cases. If you do external debugging, heap dumps, it doesn't matter. But if you have memory-intensive operations, which requires a lot of garbage collection cycles, every garbage collection cycle, minor or major, requires global save point in order to manipulate objects. And if time to save point is too big, you will slow down your execution of your application. And that usually happens if you have too long methods, for example, or too complex method or whatever, so you can monitor this TTSP and keep it as small as possible. So let's continue with our examples. This is still days in month method, the method returning number of days for particular month and year. But in this example, C2 compiler outcome. Reason, executed, still enough. We have 1 million cycles. This occurred after more than 5,000 execution. And you can see resulting assembly code here with the mapping. What is interesting after initial stack initialization, there is no more tracking, so code is simpler. For the switch structure, it uses a lookup table. It's much faster. So you have a lookup table definition, and then there is a read up from the lookup table based on the input case arguments, and then perform jump into that target read operation, which happens here much faster. And this is continuation of that. So this is again continuation of our usual target for the April month. What you can see that there is optimized branching. So the branching is not happening for that April. After April, it automatically allocate object-based integer, call the constructor if needed, and return the value. So no branching there needed because that's the most common path. There is inline TLAB allocation, so very simple here. Inline constructors, so you can see that the code is much shorter, so much faster for the execution than as a result of C1 compilation. It found no nulling is needed, some cache optimization techniques, saying I've allocated this object because usually by default all memory operations goes through L1 cache, L1 data cache. So in order to write something there, L1 cache have to retrieve the data from the L2, L3 or external memory, have it, and then do modification, and modification is after that usually lazily propagated up to the external memory. So in order to speed up this process of allocation of objects, Java came with this cache optimization technique saying prefetch. So if it allocates some small objects here in local allocation buffer, it knows that after some time it can allocate another object. So in order to speed the later allocation, it says for the CPU, do the prefetch operation, prepare the data addresses in L1 data cache in advance, do not block my execution, do the memory operations. In the meantime, still execute my code, and later, if there is another code trying to write into next memory address, it is already available in L1 data cache. That is what is happening here, cache optimization, 3 cache lines in advance. Cache line size, you should know that, 64 bytes by default, but modern CPUs can have the bigger. So 3 times that cache line size is already prefetched into the local L1 data cache. Final cleanup and so on. So the method is much simpler than for the C1 compilation. And here is a target for the default and also different versions than month 4. It's simply during the execution of C1, because there is that tracking, and in our code we always call that with the April. So it knows it was always called with the April. So do not compile anything than April. And if that happens, that's the reason here, remap input and return back to interpreted mode again and trigger the compilation. That's what is happening here. So if for some reason some different piece of the code calls later this one with different than input argument 4, remap it, recompile it for address and so on. So that's what is happening in C2 compilation as well, that risky assumption in advance. Here we are moving to the compute method of our example. The method is here. That's the one having that 1 million cycle calling our days in month. And in order to simplify that, I'm just listing here a result of C2 compilation, but for the on-stack replacement. On-stack replacement at 10 offset, Y10. Here we have our disassembled representation of the bytecode of this method. 10 is here. This blue highlight here is that 4 cycle. So at the target jump position at 10, there is a replacement of the previously, in this case, C1 result with this C2, with the better code. First, mapping of arguments using this stack map table is used into proper registers which are used in our C2 code, and then there is this C2 code inserted. So you can see testing, call of the methods, and at the end, because we are replacing just this piece of the code, just the cycle, not the end of the method, because we don't know anything about that yet. So at the end of this, we are reinterpreting back to the interpreted mode, or to the C3 in our example, C1 compiled to the level 3, and execute the rest of the method in the previous compiled version. At the same time, there was triggered C2 compilation of the whole method for the further time. So you can see, oh, okay, so there is some back edge count here, so that's the reason why it's worth to prepare C2 compilation. And in this case, it's using a combination of full inlining of the method, days in month going into compute method, dead code elimination, do not do there anything which is not needed, object escape. What is object escape? You can see here is the whole resulting C2 assembly code for our compute, including days in month. There is no for cycle, no call, nothing. There is just assignment of 30 million. Why 30 million? Because days in month is always returning 30. There is always 1 million cycle, so the accumulator O in our compute method accumulates to 30 millions. All this can be evaluated during that C2 optimization. So it's returned 30 million. No loop cycle is needed, so it's completely eliminated. Invariants are eliminated because they are not modified in that cycles. It's reducting the algebraic form because it even doesn't need to do the multiplication 30 by million, always the constant. So that's the strength reduction. Object escape. Our days in month was returning object-based integer. And in our compute method, we were extracting the value from that object-based integer and adding into our accumulator there. Object escape means do not allocate that integer at all completely. Use that constant. That's the result of the escape analysis. That happens on many cases. If you have libraries like vectors with the 2 components, 3 components, whatever, and you have a lot of objects, and if you do benchmarking of your memory, you can see, oh, if you do really tracking of allocation of new object, you can see, oh, there was allocated 10 millions of objects. That's not the truth. If you start it using standard execution without compiler, without tracking of object allocation, no objects are allocated at all. They are eliminated during that optimization technique called escape analysis. And that's the result here as well. So no object allocated. That's the key thing here. So some summarization here from the Java virtual machine performance. First, it requires, if you do measurement of your virtual machine code, it requires some kind of warm-up, because running in interpreted, after in C1, later in C2. So you need warm up your code to get a resulting code, and also you have to warm up it with your standard data you are passing usually to those methods, because you saw that it internally does risky assumptions, and compilation is based really on the data which is going into the methods. Another thing just to remember from the previous part is that the compilers cannot do all the magic. If you write wrong source code, not all techniques can easily reach their results. Even the vectorization is not possible if you write wrong for cycles which are not clearly understandable for the compiler. So that's the reason why you should really study the outcome of your code, because if you write it slightly different, it will be much more faster. Then the difference between 32-bit and 64-bit JVMs. 32-bit is no more used, but the heap size is limited. 64-bit with maximum 32 gigabyte of heap size, not the whole memory, just the heap, because non-heap can have another 32 gigabyte and so on. With the default object allocations, those 8 bytes, is much faster. Why faster? It reduces the memory, fine, but also you will better utilize your L1 caches, which are very limited. They are very expensive in the hardware, and if you have just 32 kilobytes of L1 data cache, if you save a lot of space of the pointers, everything is pointer. Everything is object usually, except the primitives in the virtual machine. If you save just the space for the pointer representation, that OOP, you are saving a lot of space in memory. Today, there are huge memories, like many terabytes we are using, etc. So that's not the problem, but the problem is still L1 data cache. which is limited. And so if you fit more data, it's then faster execution. If you really need use larger heaps, you have to consider this. You are using more space for the references, fine, you cannot do whatever. But if you, let's say, use 35 gigabytes of heap, it has no sense. Why? Because it was experimentally found that in standard application, but it really depends application to application, but if you have a lot of objects, you have a lot of pointers, a lot of OOPs. If you put there just the 35, in effect is that you are effectively using less than 32 gigabytes. It was found that you need at least 48 gigabyte of heap size to have it almost similar to 32 gigabytes, just to compensate those bigger references, not only for your pointers to objects, but also for internal class representation, everything which is inside virtual machine and perform some role of the pointer have to be 8 bytes instead of 4 bytes at that moment. So it's still wise to think about that limit 32 gigabyte, and if your application can fit there because it will be much faster. Any operation then requires some shifting, logical shifting operations. But in fact, those are in nowadays computers costing 0 clock cycles. They are done in superscalar architecture very quickly because all this shift 3 bits to the left side, just multiply it by 8, is done on registers. And whatever is done on register is done in previous phases before execution, and during execution nothing is needed at all. So the cost for the compressed OOP is close to 0, so that's perfect. But the effect of much smaller size of the references is crucial on the cache utilization side. So now let's move to the last part of our course today, and that's the profiling. You can profile either CPU or the memory, fine. Time spent in methods or usage of the memory or allocations and so on. There are 2 main modes for both profiling: sampling and tracing, with big differences. Sampling is some kind of periodic sampling. If we look from the CPU perspective, it's a periodic sampling of the stacks. So every thread has stack. Inside those stack, you have frame for every method. So if you do global save point, you can analyze the stack for every thread and infer where that thread is with its execution at that moment, and you can track that. And if you do that regularly, then you can, after some time, let's say you can do that 100 times or 1,000 times per second. At some time of measurement, you can infer, okay, my application is usually spending that percentage of time here, there, or there. It's not exact, because you can miss some internal calls. But if you do that sampling for longer time, it's high probability that you will catch everything. So it has not 100% accuracy. But on the other hand, it doesn't do any bytecode or assembly code modification. So in fact, your code is running full power with all optimization techniques I've just described. So you are not affecting the code at all. And there is just 2% impact to the application runtime itself, because you are invoking just regularly global save point, and during that global save point, analyze the thread stack. That's it. Accumulate the data and visualize it for the user. It's not 100% accurate, but it's very efficient. On the other hand, tracing, instrumentation, tracks really every method, entry, exit, allocation of the object, if that is memory profiling. Memory profiling for the sampling is doing regularly heap dumps and analyze the number of objects which are on heap and study the differences there. But tracing, if it has to track every method, exit, entry, exit, trace object allocation, it has to modify or instrument the bytecode for the first time. That instrumented bytecode, you will see on the examples, affects the optimization techniques, because you introduce a lot of additional code, which then forbids further optimization techniques like object escape analysis. not possible at all. So you will measure something which is not happening in a real execution of your application. So that's problematic. So the standard approach you should use is first start with the sampling. You can regulate the frequency of the sampling. Find some candidates of your hotspot in application where your application is spending too much time, and then focus the tracing, because the tracing could be focused with filters to particular piece of the code. Instead of tracing the whole application, just trace this method, this class, or whatever, this package. That's possible, and it will affect just that package. And you have to still keep in mind that the tracing itself could affect optimization techniques, and you can measure something different than you're expecting. One of the famous tools is Visual VM, which was up to some version of Java part of the development kit. Now it's standalone tool, but still it's open source. You can use it for whatever purposes you want. Some examples. Days of month, our example, enable CPU tracing, and you can see a lot of code was added just because of tracing of this method, because it has to collect position of the code, store it into some usually huge hash map data structure saying entering this method, that position with these arguments, etc., and it was called in this stack. And finally, just the entry tracing results into this more than 700 bytes of assembly code. So it's really the assembly code added to the method. And that assembly code affects the optimization techniques, because then the C1, C2 compiler, this was C2, but in C1 it's much worse, is affecting the optimization which are applicable there. So the same applies to the exit. For the exit, it's slightly less, but still additional code is added there even for interpreted mode C1, C2. For C2, more than 300 bytes are added to the exit of the method. This is then the outcome of the tracing. So you see the threads, and you see how many times it was there. Because it's tracing, you see really the invocations which are extremely precise, because it's tracking every execution. How many times was spent there, because you are measuring the time in that method, and so on. So, summarization. Tracing either CPU or memory allocation tracing, which is very similar to this, results into much slower code in all compilation results. So in fact, affects what you are measuring. I've already mentioned this recommended approach. Do the sampling first, identify some bottlenecks in your application, and then focus with tracing just specifically to the identified parts. And moreover, just keep in mind that warm-up of the application, that's crucial as well, because if you run the tracing from the beginning, you will be tracing interpreted mode, and that's something which is not useful. The second tool I will mention here is GMC, which is included in development kits. That stands for Java Mission Control. It contains sampling by default. If you enable this, it uses internal sampling probes which are already in virtual machine, because every virtual machine is sampling executions in C1 in interpreted mode, MDO, etc. So JMC tool can access this data with no additional cost and show you many informative stuff which can help you to identify bottlenecks of your application or hot codes and so on. So it shows you all kind of events happening, allocations. Also, because if allocation of the object doesn't fit that TLAB, thread local allocation buffer, the allocation happens globally inside virtual machine, synchronized with all other threads. And at that moment, all information can come into Java Mission Control. And you can see that there are a lot of objects allocated outside of TLAB, and what kind of objects and where, because all that information is already available. So let's summarize the approach to the application performance testing. First of all, you should not test any artificial stuff, but rather real application. ideally the way how it's used normally, because the way how you call some code affects how it is optimized, how it's then benchmarked. If your benchmark is using different data, calls different methods, result could be completely different. There are micro benchmark, just very small units are tested. You need to do warm-up to measure a real code. Just provide into warm-up the data which are usually there. You have to consider the compilers. Synchronization is affecting code as well. If you do your micro benchmark just for the simple piece of the code, one of the optimization technique inside Java is eliminate synchronization if it is not needed. So it's eliminated. You have single-threaded testing. But if it is in a real world using multi-threaded execution, cannot be eliminated, then the synchronization takes a role and could affect execution. So all this could be affecting your benchmarking approach. On the other hand, macro benchmark measure on the level of the application or the module input and output level, not focusing on single units or some simple pieces of your application, just to measure everything, the whole application. And also you have to understand the throughput, elapse, and response times. In Java, the major effect on the execution, aside of the optimization techniques used for the compilation, is garbage collection. Because if your application, which is usually the case, is using dynamically created objects, a lot of objects is created there, garbage collection have to run, and then the configuration of the garbage collector itself can affect the performance and the benchmarking of your applications. A recommendation, you should use existing generators of the data and testing rather than writing your own, because usually your own testing case will be not that good like some general one, and you will manifest all these kind of issues I've already mentioned. You should understand the variability changes over the time of your application, because usually there could be some internal state, either internal or external in databases. And if that state grows up, data structures are bigger, then could be slower, and so on, the execution. So there could be also some background effects, load, networking, and so on. You should work with the uncertainty during the testing, so some kind of probabilistic approach should be used. And the last recommendation I have today is test early and test often. It's worth to create even the unit test, which simply test very small piece of code, but measures the performance and accept it. It should be really fast, not to bother with long testing all the time, but it will bring benefits. If you automate tests, script them, have proper test coverage, and test with the real arguments, it will bring benefits, especially in more complex codes. And that was the very last slide I have today, so thank you for your attention.